Okay, so good evening, everyone. I am Moina Ghoshal. I am assigned as the TA. Just a second. Yeah, so I am assigned as the TA for this course, which is entitled as Fundamentals of Spectroscopy, which will be which was instructed by Professor Sayun Bakchi and Professor Anirban Hajra. And this is the questions regarding assignment of week 6, where I am going to solve some problems regarding this week assignment. Like in this week, there was a discussion on rotational vibrational spectroscopy and some spectroscopic features of from the quantum mechanics, which was very well derived and very well explained by Professor Anirban Hajra. So in this week, we will solve some problems regarding that part, and then we will understand that how quantum mechanics is related to this. From this quantum mechanics, how you can calculate these spectroscopic parameters or these spectroscopic terms. Okay. So for that we need to know what was taught in the last class. Very in the very with very basic introduction, I will explain you that what was actually taught. So it was about the previous week's assignment, which was discussed like yeah. So there was a discussion on vibrational spectroscopy. What was discussed about vibrational spectroscopy? It was shown that IR regions of the electromagnetic spectrum is actually responsible for IR radiation or vibrational transition. Okay, and this IR radiation can be derived into three parts: mid IR, near IR, far IR. Okay, so near IR, that means this near IR will have, you have seen in this electromagnetic spectrum that this energy of this near IR is close to UV. Okay, then next is middle IR, and then there is far IR. Then there was a discussion on Hooke's law. What is Hooke's law? And there was a discussion on harmonic oscillator model. There was and there a spring was considered, and then it was discussed that this new bar was found to be 1 by 2 pi c root over of k by mu. It was also discussed. Okay. Then there was a discussion on how the parabola or the potential energy curve, parabolic potential energy curve, actually changes with force constant. Okay. So this discussion was, suppose this is my potential energy and against R. Suppose this is my V of R and this is my R. Okay. So if the parabola was like this, what will happen if we increase K? It was shown that it will be much more steeper with increasing K. As we increase more K, it will become much more shallower, much more steeper. Okay. So all this was discussed in the previous class. Here from there to there is increase in K. Okay. So it was discussed that how the force constant actually affects the parabolic potential energy curve. Then there was a mathematical proof for this dependence of force constant on this potential energy. What I have talked in the last point, there was a mathematical derivation. It was shown that this K was defined as d2v by dr2 at R equals to R equilibrium, right? It was discussed also that the force constant is actually double derivative of potential energy with respect to R at R equals to R equilibrium. Then Then there was a mathematical calculation for the energy of this harmonic oscillator, right? So how was the energy of this harmonic oscillator? The energies of the harmonic oscillator was discussed. Suppose I denote this vibrational quantum number as V. So, and ask, okay. So for clarifying, for clarity, we will just use this N. So this En is nothing but is equals to N plus half H nu. Okay. So this is the energy of the harmonic oscillator. That is the suppose this is the potential well. So these energy levels are divided in plus half H nu. So the ground level will have energy half H nu. Next level will have energy n equals to 1 level. So if I draw it, suppose okay, so let me erase this. Suppose okay, yeah. Suppose this is my harmonic oscillator potential well, and these are the energy levels. Just clearly see these energy levels are equal. This is half H nu. This is 3 by 2 H nu. This is 5 by 2 H nu. This is 7 by 2 H nu. So the difference between them is always constant. How much is this? This is nothing but H nu only. Okay. So the difference between two energy levels when we are considering simple harmonic motion, this energy difference is only H nu. Then there was a calculation of energy difference. Then there was the derivation of selection rule. Sorry, for harmonic transition, and there two things are discussed. One is gross selection rule, another is specific selection rule. What is the gross selection rule? Gross selection rule states that there should be a change in the dipole moment, which we will discuss today also, that d mu by dx will be not equals to 0. That means suppose I have a molecule which has permanent dipole moment initially. Suppose the molecule has a dipole. Okay. Suppose the molecule I have is A, B, this molecule, I think, suppose there is delta plus charge, this is delta minus charge. Suppose this is a dipole, okay? So, since it is a dipole, can we say that it actually shows vibrational transition? No, we cannot say that because there should be a change in the mu. There is a dipole moment initially, suppose I am denoting it as mu. So there should be a change in the dipole moment, that is d mu by dx will not be equal to 0. And under that condition, under only that and that condition, your vibrational transition will happen. So this is called gross selection rule. Then another selection rule is the specific selection rule, which says that your delta nu or sorry, your delta v should be plus minus 1. Delta v should be plus or minus 1. It is a specific selection rule. That means there should be a change in the vibrational quantum number by 1 unit. That means transition from v is equals to 0 to v equals to 1 allowed. But v equals to 0 to v equals to 2, v equals to 0 to v equals to 3 is not allowed. Just only, just like the same thing, v equals to 1 to v equals to 2 is allowed. But v equals to 1 to v equals to 3, 4, 5, 6, etc. not allowed. This is called harmonic oscillator problem. Okay. That means for harmonic oscillator, only these are the criteria that the total energy will be half h nu, or sorry, n plus half h nu. The difference will be constant h nu. There will be two selection rules for corresponding to this. One is gross selection rule, another is the specific selection rule. Gross selection rule states that there should be a change in the dipole moment whenever there is undergoing whenever there is some vibrational transition. Specific selection rule states that the permanent dipole moment should be non-zero. Sorry, the specific selection rule states that this delta V should be equals to plus minus 1. And then there was a derivation of the selection rule from transition moment integral. that this the same thing was discussed in this week's lectures also, that if you want to derive this selection rule, you can find that, and you will face some condition where you need to satisfy the condition that delta v is equals to plus minus 1. Under this condition, you will find that your transition moment integral value will be non-zero, and if this is non-zero, only then this transition will happen. Vibrational transition from one state to another will happen. Okay, so this is the conditions. Then it was shown that if harmonic oscillator model is correct, but in the reality the things are not the same thing, right? Because it is an approximate model. Since is that, then there comes anharmonicity, which says that in the initial stage the parabola becomes, suppose it is my when if it is my harmonic oscillator potential, and then anharmonic oscillator, it says that it is much more steeper in the values for r less than rq, but it becomes much more shallower when r greater than rq. So if this position is r is equals to rq, it says that in the initial stage, suppose I am okay. Let me draw it with another colors, then you will be understand. You will understand it clearly. Yes, this is the harmonic oscillator potential energy. Now I am drawing it with the other color. You can see now I am drawing this anharmonic potential, which is much more steeper in the initial stage, but there will be saturation. Okay, so if I name it VR, and this is R, and this position is R is equals to R equilibrium. R suffix equals to R of equilibrium. So at that point, you can see that if R is less than R equilibrium, the potential energy will be shallower, and if sorry, the potential energy will be stiffer. But if you increase your R, and if this condition is satisfied that R is equals to R equilibrium, then the potential energy curve will be shallower. Hmm? So this is for SHO, this is for ANHO or anharmonic oscillator. Okay. So you can see that when this approximation is changed from harmonic to anharmonic one, you can see for R less than R equilibrium, this region is R less than R equilibrium, and this region over there it's R greater than R equilibrium, and you can see that when R less than R equilibrium, this is much more stiffer, and when it is getting much greater than R equilibrium, then it is becoming much more shallower. And then there was a discussion on potential energy surface in terms of Morse potential. This is called Morse potential. It was also discussed. And then there was a change in the vibrational energy levels of a molecule due to anharmonicity. It was also discussed that how anharmonicity will change the energy level distribution, or the distribution of these energy levels of this molecule when there is anharmonic oscillator. If you consider harmonic oscillator model, and you have seen that the case where for simple harmonic oscillator, for which the energy difference was h omega or h nu, it is not true for anharmonic oscillator. It was shown that if this is the potential energy diagram, yeah, So if it was discussed that if you are going more and more with energy, these levels are becoming much more closer to each other. Okay. So nanonomic oscillator says that if you go with high vibrational quantum numbers, your energy levels will become closer. The difference between the energy levels will gradually decreases. How this will decrease? This was also discussed that there will be a term of h nu e x c or chi e. This term will actually decrease the energy. And then there was a discussion on the shape of this potential energy curve for an harmonic oscillator. How this is mathematically related. There was a tried exponential d3v dr3 term which it actually denotes that how should be the shape of this potential energy curve. And then there was a discussion of fundamental transition, overtones and hot bands. So what was fundamental transition? Fundamental transition is the transition from v equals to 0 to v equals to 1 level. This transition is called fundamental transition. And the other transitions were overtones and hot bands. What are overtones? Overtones are from v equal to 0 to v equals to 2, 3, 4, any transition is possible with overtone. Okay, it will start from v equals to 0 and you can go higher up to any level. This is called overtone. And hot band is a transition from v equals to 1 or any higher energy level to suppose v equals to 2, 3, 4, any other from higher energy levels to higher energy level. This transition occurs, this is called hot band. So this was all about vibrational spectroscopy. That was discussed in the and some problems regarding that also discussed about in the previous live session. So today I'm going to discuss something which is beyond vibrational spectroscopy, which is called raw vibrational spectroscopy. So raw vibrational spectroscopy. It was shown that for CO means carbon monoxide in CCl4, you can see there is with this appearance of this vibrational line, there is some appearance of these rotational lines also, and and this explains that these rotational energy levels are very quite close to this vibrational energy levels. So, so it is shown that for any transition there is some electronic energy level with under which vibrational energy levels are there, under which there is rotational energy level. So this is you can just remember these things. Suppose this is my vibrational electronic energy level. So this is my vibrational level. This is v equal to 0, v equals to 1, v equals to 2, any other levels, okay? And under this there are certain rotational levels, very close in energy. Okay? So this is the electronic level, this is the vibrational levels, this is, and so electronic levels are consists of very large number of vibrational levels, okay? And these vibrational levels consists of rotational levels. So, so when you are going to describe something, that's like when you are getting electronic spectroscopy, you will go to electronic spectroscopy, you can see that under electronic spectroscopy, you can actually get the vibration of a molecule or vibrational energy levels position of a molecule. Just like the same thing, if you are going to analyze some vibrational spectra, you are definitely there is a chance that you are getting to rotational lines. And so the appearance of this rotational level in the spectrum which was also discussed in the terms of rotational vibrational energy. And then there was a discussion on dissociation energy, and there was also discussion on the appearance of vibrational levels along with rotational levels in the potential energy diagram, which I have shown you here. And what about the dissociation energy? It is shown also that the true dissociation energy, that means with equilibrium dissociation energy, should be followed by your dissociation energy plus there is some term which is called 0 point energy, and this term is not zero. So, for getting to this two dissociation energy or the dissociation energy at equilibrium, you need to find this d0, which is the 0 point energy theoretically, and you have to add this with 0 point energy that you will get from half h nu in this half h nu, or half h nu minus half h nu exc, these kind of things, which will depends upon which kind of oscillator you are taking. Okay. So in the next lecture, it was a discussion on Born-Oppenheimer approximation. This was just very early discussed. Born-Oppenheimer approximation. This Born-Oppenheimer approximation, actually they told that rotational and vibrational energy levels, you can treat them separately for calculation. Okay. So whenever there is some rotational and vibrational energy levels, you can treat them separately. This is Born-Oppenheimer approximation. You will get to know about this much later. Suppose in a very basic way, suppose you are considering the motion of electron and nucleus. Okay. So you know nucleus mass is much more. Suppose compared to electron, the mass of the nucleus or the protons is much more. So with compared to electron, I can say that this motion of this nucleus is fixed. So this is kind of a Born-Oppenheimer approximation, that we can treat this electron and this nucleus separately because they did not affect their each other's potential, each other's in mass. That is the way I'm just going to tell you. This is an example that this Born-Oppenheimer approximation tells that we can just treat these rotational and vibrational energy levels separately, which was beneficial to calculate the selection rule for vibrational transition, rho vibrational transition, which was discussed that for considering this anharmonic oscillator approximation, the vibrational selection rule becomes plus minus 1, plus minus 2, plus minus 3, plus minus 4, dot. And along with that, since you are considering this rotational vibrational transition, there will be another transition corresponds to delta J is equals to plus minus 1. So what is this transition? You know this. This is the rotational selection rule for rotational transition. Okay, so when you are considering rotational vibrational variation equally, then you have to consider both vibrational selection rules and you have to merge that. Okay, so and there was a discussion on appearance of P branch and R branch linked to vibrational spectra, and it was shown that considering these two, this condition is satisfied, then if there is a transition from J to J prime level, and if J prime delta J, which is equals to minus 1, will get P branch line whose energy is much more lower than fundamental transition. And if delta J is plus 1, so if delta J is equals to plus 1, then you will get R branch line. So we can see here that there is an appearance of P and R branch in the rotational vibrational spectrum. Okay. Now from this there was a sudden jump to the quantum mechanical description, or there is a derivation for this rotational vibrational spectroscopy or vibrational spectroscopy. And there is a discussion on this classical description of simple harmonic oscillator. Simple harmonic oscillator's classical description is F is equals to minus X, F proportional to minus X. It is restoring force proportional to the displacement. How far if you displace, the more force you need. Okay. So this is the classical description of simple harmonic oscillator. Now quantum mechanical description was also introduced, and for that there was, and you know how to calculate this. For that you need to find this H dagger H operator, that is the Hamiltonian operator, which is of kinetic energy and potential energy operator. So for this harmonic oscillator case, if you know this kinetic energy and you can know this potential energy, if you merge it and you then solve this Schrodinger equation, you will definitely get your psi 0, and this, since your psi will be an eigenfunction, you will get the eigenenergy E0. Eigenvalue E0, which is your E, which is your energy. Okay. And this was also very well described by Professor Anirban Hajram, who has described this very beautifully. If you have not seen it, you can see it. This is the derivation of this wave function and energy. Then there was a calculation of energy difference between two energy levels in the right of two operators which was discussed here, B and B dagger operator. So B operator and B dagger operator. Which are these operators? This is ladder down operator, this is ladder up operator. Okay. Now this ladder up and ladder down operator, this means it will increase your energy from 1 unit. If you are in psi state, if you have applied this ladder operator, you will lead to your next stage or your up stage. Similarly, if you are in a certain stage and if you apply ladder down operator, then you will reach to this lower level. So this is called, then since this is related to the step jump, so it is called ladder operator. In the next lecture, there was a discussion on the finding the wave function of this harmonic oscillator. This was found considering the lowest energy to be 0, and then if you solve this, you got this value of psi 0. What is psi 0? Then if you know this psi 0 and if you know this concept of how ladder operator works, you can apply ladder up operator. Just what I have said, I said earlier that if you apply this ladder up operator, it will lift your energy up. So you will reach from state psi 0 to a state psi 1. Similarly, if you apply another ladder operator and find energy for the next level, you can see that you can reach from E1 to E2 level. Okay. And then there was a discussion of the normalization constant, and also there was some discussion about the graphical description of wave function, how the wave functions looks like. Okay. So for different values of these quantum numbers or vibrational quantum numbers, how this how will be the graphical presentation of this wave function, this was also shown. And the next lecture, there was a description of total kinetic energy in terms of center of mass and relative coordinate. That is total kinetic energy TKE. I am writing total kinetic energy, which is denoted by T, which is half m1 x1 square x1 dot square plus half m2 x2 dot square, which was converted to half m dot x m dot ne, will be m x1 square dot square plus half mu small x dot square. That is, if your which the coordinates of the atoms is converted to a center of mass coordinate and relative mass coordinate. Okay, and you can see there are two terms, that is this m over here and this mu over here. Okay, so these two terms represent center of mass and the relative mass. And then there was a discussion that how to get the selection rule for vibrational transition. And it was shown that to prove that the selection rule, you need to consider transition moment integral. What is transition moment integral? There is upper state, there will be mu, and there will be lower state. So this psi I, psi f, transition moment integral, that means you have to find this value. This if psi f is your final state, you have to find this value. That's from psi f to psi I, if there is, this value is non-zero or not. For that case, you have yes, Professor Anivan has shown that if you are going to calculate this, we will find that some condition will arise when your delta n will be not equals to need to be plus minus 1. Otherwise, this will be not possible. And it was also proved using this ladder two ladder operators, ladder up and ladder down operator, which was very well described in this lecture. So this was the course content for this week. What I have discussed so far, there was a discussion on rotational vibrational spectroscopy and quantum mechanical description of how these vibrational selection rules, vibrational energy, this concept of harmonic polynomials, another concept this was introduced, how these are coming from quantum mechanics. So this was the course content. Now I'm going to solve some questions regarding this and I will show you how to solve this, that will be beneficial for you to solve your assignment. So that, let me check if there is anybody or not. Okay, nobody is there. So, what I'm going to ask, the first question is, in the classical description of an isolated simple harmonic oscillator, the total energy, what will be the correct option? That the total energy does oscillate with time, total energy is constant, it decreases with time, and has a certain minimum value and can never be exactly zero. So, this is the question. Whenever this type of questions will be asked in this sorry, the classical description of an isolated simple harmonic oscillator, you first, yeah. So in kinds of question, I have told you that you first need to consider that this is a isolated simple harmonic oscillator. So you have to find your energy of the system, and if you have to see if this is changing with time, or it is decreasing with time, or it is constant, or it has a certain minimum value and can never be exactly zero. So you can find this reference in the lecture number 29, where it was discussed that what should be the energy total energy of this isolated harmonic oscillator. So this is the explanation I have written here, that in the classical description of simple harmonic oscillator, the total energy of the system is the sum of kinetic energy and potential energy. So what is the potential energy? Classically, V of x, I can write it as half kx square. Now you know what is x. X is nothing but x0 cos omega t, right? And if you put it, half k x0 square cos square omega t. This will be the energy, potential energy, that is half k x0 square cos square omega t. So this will be your potential energy, P of x. Yeah. Now, if you are going to find this total energy, that is sum of kinetic and potential energy. The kinetic energy, you will find that your kinetic energy will look like this one, the same thing. Just this cosine will be replaced by sin function. Okay. So what will be your total energy? Total energy will be sum of kinetic energy and potential energy. Now I am putting the values of kx0 square sine square omega t plus, there should be half k x0 square cos square omega t. If I take this half kx0 square common, kx0 square common, there should be sine square omega t plus cos square omega t. So you know from this trigonometry that sine square omega t and cos square omega t, and if you add this up, it will give you 1. So the total energy will be kx0 by 2. So there will be no dependence of time, on there will be no t term here. So I'm writing it freshly, that what will be your total energy of the system if you consider the simple harmonic oscillator case in the classical system, that your total total energy should be equals to k x0 square by 2, right? So you can see here there will be no t term for this total energy. That means there will be no dependence of time on this total energy. That means with time you can see that total energy is not changing. So I can write this conclusion as this total energy of the system is unchanged with time. So, what should be the answer? The answer should be the total time will be constant. Okay. So, you can see here that whenever you have some classical description of simple harmonic oscillator, you can see that total energy is constant. How it is constant? You can calculate what is the total energy. Total energy is the sum of kinetic energy and potential energy. Now you know what is your kinetic energy. Okay. Now, yeah. So, kinetic energy, you know, this X can be defined as x0 cos omega t. Suppose when you are so if you, from here you can get this Vx half k x0 square cos square omega t. Now, when you are calculating this kinetic energy, you need to know, you know, what is kinetic energy, half mv square. And if you would put the value of V is nothing but dx dt. So, if you get this dx dt, you know your x is x0 cos omega t. So if you take its differentiation with respect to d, that is dx dt, you will get there will be a sine term. Okay, there will be a minus sine omega t, which will multiply by omega, and then from m omega you can get this k by the relation omega equals to k by m. Okay, so for this clarity I can do this for you, that your kinetic energy total is equals to half m v square, and which is defined as half m dv dt. So, sorry, dx dt square. Now you know what is your dx dt? This will be x0 sine omega t. So if x is this, your dx dt will be x0 into omega into minus sine omega t. That means minus x0 omega sine omega t. This is your dx dt. Now I have to put that here. So if you know that whenever I'm getting squared, this minus will cancel. So if we left with half m x0 squared into sine square omega t. Oh, sorry, that should be an omega t square term, x0 square into omega square into sine square omega t. Now from this I can write half x0 square into m omega square into sine square omega t. From this, if you know this relation that omega is related to omega equals to root over of k by m. So if you square it from the both sides, you will get k by m is equals to omega square. So then this you can post it this omega square by as k by m, and this mm will cancel out. Okay. If you put omega square in place of omega square, you can write it as k by m. This mm will cancel out. So you will left with this only k. So this will become half k x0 square sine square omega t. So this is the your expression of this kinetic energy. What I was talking you about, this kinetic energy will come at half k x0 square sine square omega t. So if you take total energy, this t plus v, if you get that, your total energy should be half k x0 square. So which is independent of time. So total answer will be the time, the total energy will not change with time and is constant. Okay. Now I'm moving to the next problem, which I am going to discuss. So the problem is that in the quantum description of simple harmonic oscillator, the quantum description, now from this, there is a sudden jump from classical one to quantum mechanical. So in the quantum description of simple harmonic oscillator, the energy gap between two successive eigenstates. What will be the description of two successive eigenstates? And the options are that it will increase with increasing quantum number, it will decrease with decreasing quantum number, is independent of quantum number, and is zero when the transition dipole moment integral associated with two states is 0? What should be the answer? So for this, to calculate this one or reply to this, I would like to say that you can find this answer in the lecture 29. Just you need to know about ladder operators. If you know this concept of ladder operators, you will be very easily going to solve this problem. Huh. Okay, so yeah, so I've written the explanation that in the quantum description of simple harmonic oscillators, it has shown that the energy difference between two successive levels is h cross omega or h cross nu, whatever you can write. You want, you write it. Yeah. So it does not depend upon what will be your quantum numbers. That means you know it from if you've done this assignment or if you've done the course on this vibrational spectroscopy, that if you consider simple harmonic oscillator approximation, the energy difference, suppose it is my v equals to 0, this is my v equals to 1, this is my v equals to 2, and if this is my v equals to 3 state, you know the energy they have between these two is always h cross omega. Whatever be the difference between two successive levels, wherever it is, it will be always h cross omega. Right? So this you know from spectroscopy that you know the energy of some levels, that is you know the energy of some vibrational level, and if you just subtract this energy, you will get the energy difference between them, and you will find it will be h cross omega. But in this lecture, what you have to show, that you can show, I can show the same thing with the use of ladder operator. Now, what is ladder operator? Ladder operator, you know, ladder operator is defined as b dagger and b. B dagger is defined as 1 by root 2 minus of d dq plus q. This is ladder operator 1. Another ladder operator was b, which was defined as 1 by root 2 d dq plus q. Okay, so this was the ladder operators. And what is q? Q is also defined as root over of m omega by h cross x. So x is related to q, and this from this q I can write my Hamiltonian, my ladder operators, and how this ladder operator is related to my Hamiltonian. You know, the relations are all there. That is, your Hamiltonian operator should be like, you can write it as h cross omega b dagger b plus. You know this. This is the Hamiltonian operator. And for using this, the energy levels of the vibrational levels, that was also solved. Now, I am not going to the detailed derivation of these energy levels. What I am going to emphasize is that if you just go through it, and if you, after solving these equations, you will come up with something like, there will be some equation which will show you that, suppose this is my Hamiltonian operator, it is operating on my b dagger side, it will give me e plus h cross omega b dagger side. Okay. So, so if you operate, so if it is satisfying, you can see here it is satisfying Schrodinger equation. So if psi is an eigenfunction of the Schrodinger equation, then b dagger psi will also be an eigenfunction. Now, if you find, you can see here the energy will increase by h cross omega. Now, it was also shown that same equation we will obtain if double b dagger will be there. Suppose for B dagger psi you will want to get another psi which is much above this B dagger, you will see that this equi energy will be plus 2h cross omega. So you can see here that the total energy will be getting increased by h cross omega unit as much as suppose I am here. So I am saying that if psi is an eigenfunction, b dagger psi is also eigenfunction. So whatever I am doing, I am using my ladder operator. What will it will do? It will increase my level. It will change my state to another high level. Which level? This that level which will have energy of E plus H u or E plus H cross omega. Okay. So into this level, so it will put me into this level. Yeah. So it will put me into this level, E, which has energy E plus H cross omega. Now, now I'm doing another ladder of operator on this above newly created excited state, which has energy E plus H cross omega. What I have talked about here. Now, if you do this, you will find the next higher energy level will be E plus 2H cross omega. Okay, so we will find another B dagger will be there. Okay, so there will find that the energy will be increased by H cross omega unit, and this clearly demonstrates you that the energy difference between two states will be H nu or H cross omega. Okay, so I'm writing the conclusion here that the energy difference between two states equals to always it is H cross omega. So you can see here that this energy difference is constant, and you can see it depends upon this omega frequency. Okay, there will be no term containing this V or vibrational quantum number. Is there a term? No, no terms are there. When you are subtracting it, there will be a display. There will be a difference. There, the V term will get cancelled, and there will be no vibrational quantum number term. So we can say that the energy difference between two successive vibrational levels are independent of the quantum numbers. So in this case, the answer is the vibrational energy gap, the gap between two successive vibrational energy levels is independent of the quantum number. Okay, so you can find the answer, and also in lecture 29 you have seen that that the energy difference between two states is always constant. It is h cross omega. Now I am going to the next question, which is one of the following statement is incorrect. That means that is wrong. So select the incorrect statement. So you have to find there are four statements out of which three statements are correct. One statement is wrong. You have to find that one statement and you have to just mark it. So question is the Hamiltonian associated with a simple harmonic oscillator. Problem is quite simple for simple harmonic oscillator. Yeah. So you can find this answer also in lecture number 29. Here is also discussed that the Hamiltonian associated with a simple harmonic oscillator, what should be its condition? That is, does it has real eigenfunctions? Is it time dependent? Is generally written in dimensions of coordinates while using the method of ladder operators to obtain its eigenvalues, and or I has eigenfunctions which tends to zero at its boundaries. So the explanation is here. I am written that the Hamiltonian of a simple harmonic oscillator is the sum of kinetic energy and the potential energy operator. So we have seen this Hamiltonian operator is the sum of T plus V. So what is T operator? T operator is nothing but h cross square by 2m del 2 del x2, or in one dimension I can write it d d2 dx2 plus half kx square. For for harmonic oscillator, this potential energy is nothing but half kx square. Okay, so this is the point what I am going to make, and you can see here this is time dependent or independent. It will be time independent. There will be no time dependent part. Okay, this will be always time independent. Okay, so you can see here that is that the total Hamiltonian is time independent. And if suppose there was some equation you have seen, that what is Schrodinger equation? Schrodinger equation I can write it as I h cross del psi by del t is equals to h psi. Okay, this is the Schrodinger equation, and this equation will reduce to, this is time dependent Schrodinger equation TDAC. So reduce to, it will reduce to time independent Schrodinger equation under the condition, only one condition, that and time independent Schrodinger equation will be h psi equals to h psi. This is time independent Schrodinger equation. Only one condition you need to fulfill, that h is time independent. H is time independent. So on the, if this condition is satisfied, then you can say that if your total the time dependent Schrodinger equation, you can convert it to time independent Schrodinger equation. Okay, so so I have clarified only one option of this, that is this option. You have got this answer that it is time dependent, which is written, it is really not time dependent, and you have to find that which one is the incorrect option. You have got this answer. But now you need to show that why this is the incorrect answer. That means if this is the incorrect answer or the second option is incorrect, then there is naturally that all the options are correct. You need to verify that. Okay, so I'm going to verify that. First of statement is has real eigenvalues. So for simple harmonic oscillator case, since H is time independent, since H is time independent, so you know that this time dependent equation will become time independent equation, and H psi will be H psi. This is a simple thing, that H psi will be H psi. And now, if considering this, if you are going to solve this, and this eigenvalue equation has eigenvalue of energy eigenvalues. And from your basic concept that energies cannot be complex, it will always have real eigenvalues. Okay, and these eigenvalues also will have only energy eigenvalues. Okay, so if you operate your Hamiltonian on this side, you will always get your energy, which is a real value. That means you are going to always get real eigenvalues. That means this statement which is written here is correct. Next statement I have explained that the third statement is generally written in dimensional coordinates while using the method of Lazard operators to obtain its eigenvalues. So how this Hamiltonian is related to the ladder operator? It is related as, I can write it as this ladder operator form, this H cross omega B dagger B, this will be B dagger B. Yes, so this is the way that your B dagger B is related to Hamiltonian operator. Okay, so what is written here is generally written in dimensional coordinates using dimensionless coordinates using the method of ladder operators to obtain its eigenvalues. Okay, suppose so. Just for your clarity, this H cross omega is nothing but your total energy. Okay. So, and if you multiply this, it will be your half, and this term will need to be something which will be multiplied with energy to give this energy, because you cannot add this energy with energy. Okay, so it must be a dimensionless quantity. It was also shown that when you are expressing this h and you using this ladder operator, this b dagger operator, it was described as 1 by of root 2 minus the ddq by q plus q. Similarly, this b operators will be look like this: 1 by root over of 2, it will be ddq by ddq plus q. This minus sign and plus signs will be just different for this b and b dagger. You can see what is q. Now it was explained also in the lecture that when you are going to discuss, you are going to solve this problem, you are just assuming a coordinate q. When q is written in terms of x, and you are shown now. Okay. So I'm going slowly. So I'm taking another other yeah. So from that, I'm going to find q. Q is approximated as m omega by h cross x. So if I'm going through this, we will always get something like the dimension of length inverse. Okay, and x you know distance for length. So if you multiply this, you will be q will be dimensionless. And since your ladder operators which you are using here, or by which you are constructing your uh, what you say Hamiltonian operator, these ladder operators are made of some quantity which is dimensionless. So then must be dimensionless. Suppose I am adding two things which are completely dimensionless. So the added product which I will get, it will be also dimensionless. So your ladder operator will be dimensionless. Okay. So your correction, what is written here is correct. Written in dimensional coordinates. Okay. And the fourth option is have eigenfunctions which tends to zero at boundary. Oh, sorry. This will not be ticked. This is correct option. So, but here you have to mention that it was mentioned that you have to just mark these incorrect options. So, the fourth option is has eigenfunctions which tends to zero at its boundaries. So, what should be the eigenfunction here? Here, eigenfunction is psi, and the condition of psi, that it will satisfy this boundary condition, that it will be zero at its boundaries. This is the condition of psi. You have learned, when you have learned this particle in a box, there was a condition that under that the psi will be zero at the boundaries. Okay, this is moving that, just like simple harmonic oscillator, like this kind of thing. You are seeing that the particle moving like this. Okay, so it is not going up outside. So at your the surface, or at when x equals to a or x equals to 0, your potential, your wave function is 0. This is a non-existent within that. So correct answer only. That means in this case correct answer, but actually what is said that you have to mention this incorrect answer. This is time dependent. Sorry. It should be time dependent. It is written, it should be time dependent. If it will be correct, then all the options will be correct. Okay. So this is the fourth question I'm going to solve. So the eigenfunctions of the harmonic oscillator Hamiltonian, the eigenfunctions of the harmonic oscillator Hamiltonian operators are: is this a quadratic function, sine function, eigenfunctions of the B dagger operator, or eigenfunctions of the B dagger B operator? So what should be the answer? So it was also discussed in the lecture number 29. that what should be the eigenfunction of this harmonic oscillator Hamiltonian operator, and using the B-Dagger and B operators, it was shown that the Hamiltonian operator can be written as what I have shown you. This Hamiltonian, you can write it, I am writing it here. This Hamiltonian, you can write it as H cross omega into B-Dagger B plus half. Okay. So, so at this first question, is this a quadratic function? Need not necessarily be a quadratic function. Is it a sine function? No. Psi need not to be a quadratic function, neither a quadratic function nor a sine function. It could be anything. Okay. But the next two options you have to say that the what suppose so you can write your Hamiltonian in the term of the this one. So whatever be the eigenfunction with respect to Hamiltonian, this will be the same eigenfunction with respect to this one also, right? So what will be the Hamiltonian eigenfunctions with respect to Hamiltonian? Your eigenfunction respect to Hamiltonian is also an eigenfunction with respect to B dagger B, right? So your answer, you have got this. The answer will be the eigenfunction of B dagger B operator, but it will not be the eigenfunction of only B dagger operator. Okay, it was shown that if you calculate this B dagger B, it has shown that if you calculate this B dagger and B, you can write your Hamiltonian in this term, that H cross omega is equals to H dagger is equals to H operator H is equals to this one, H cross omega into B dagger B plus half. So this is the way you should approach it. That whatever is the eigenfunction, psi be anything, let psi be anything. Okay. So whatever be the eigenfunction for your Hamiltonian, this must be the eigenfunction of your B dagger B, right? So this is the correct option, your option 4. So this will be your correct answer. So this is my fifth question. Question says that if a diatomic molecule stretches by a distance x relative to its equilibrium geometry, the magnitude of this restoring force on each atom is, which will be the correct answer? Is equal, is proportional to x square, is proportional to the mass of the atom, equals to 0. Okay. So you can find this answer in the lecture number 31, that due to displacement x relative to the equilibrium geometry, the restoring force on each atom will be equal. Okay. So suppose this is my diatomic molecule. Okay. So if it is stretched by an distance x relative to its equilibrium geometry, suppose it is stretched like this. So it is your new diatomic molecule. Okay. So if it is stretched like this, the restoring force will always be, so it will try to come back here. So since this is a symmetric stage, only symmetric stage is possible for diatomic molecule. So if you are symmetrically stretching it, that will be always equal. So it will try to always come back equally. So the force that will be always equal on these two atoms. Okay. So which what I have said, that if you have a diatomic molecules of suppose two masses m1 and m2, and if it is vibrating, suppose Now if you are stretching it and then it will, you are just leaving it and it will going to come back. So the restoring force will be equal for both the atoms because only symmetric stretch is possible for the atomic molecule. Okay, so this is the answer should be equal. Is written here. Is it proportional to x square? No, never. Proportional to mass of the atom? No. And is it zero? Nothing. So answer will be equal. Now for the next question, for a diatomic molecule where x is the distance between two atoms, transition dipole moment involving two vibrational states is always zero, can be zero or non-zero, proportional to intensity of a vibrational transition, is always non-zero when the two states have quantum numbers that differ by 1. So you have to find the correct answer. So you can find this thing in lecture number 31, where Professor Anirban Hasra has discussed this, that what should be your transition moment integral. So transition moment integral involving two different vibrational states is defined as, yeah. So transition moment integral TMI defined as this one. Okay. So I am writing it transition. Okay. So transition moment integral. Okay. This is a very important thing that I think I have need to discuss this always, whenever I am taking these lectures. So when you are going to find your psi f star mu psi I, suppose there is a transition from psi equal to j and you want to know if this transition is feasible or not. So then you need to calculate this transition moment integral. So for this diatomic molecule from psi I to psi j to psi f, when there is a transition, so I can write it as psi f star psi 0 psi I d tau plus the first term will be d mu by dx, which will be x equals to 0, and there will be a term psi f star mu 0 psi star x psi f, sorry, psi I. D tau, yeah. So this is your expression for transition moment integral. Okay. To find this, this first term. Now I am using another color to explain this. This was also discussed. This first term, which is written over here, psi f star psi 0 phi I mu 0 phi psi I d tau. So this mu 0 will go out. What will be psi f psi I d tau? This will always follow this condition of orthonormality. So this will have no contribution. Okay. So this will have no contribution. This will due to orthonormality condition. Either it will be orthogonal or it will be normalized. Okay. So for tripartite transitions, so I have said that for calculate this one, you mu 0 will go out. Okay. So you will left with psi star psi I d tau. Okay. This first term will cancel out. Now, so the transition dipole moment due to will depend on these two terms. This is related to the cross selection rule. And this is related to the specific selection rule. So you know that these two terms are there. So this and this term. Okay. So now I am going to. So you can see here that your transition moment integral will depend upon two factors. One is this factor, this change in the dipole moment at x equals to 0, and the second factor is psi f star x psi I d. Okay. Now, sorry, you're gonna, yeah. So There will be no x here. This will be r minus r 0. Just you just consider this, that x equals to 0. That means r equals to r equilibrium. Okay. Here suppose it's r equals to r equilibrium, and here x equals to nothing but r minus r equilibrium. Okay. So considering that one, you can see your selection rule will depend on these two factors, and transition moment integral will also depend on these two factors. Okay. So now what will be the correct statement? This first option is always zero. Is it always zero? No, it is not always zero. If it is always zero, then how will the transition happen? They will not see any spectroscopic transition. Okay, so it cannot be always zero. Can be zero or non-zero. Yes, it is correct. It can be zero. It is non-zero. If it is zero, then this transition will be forbidden. If it is very non-zero, then you can see this transition. It's proportional to the intensity of a vibrational transition. No, you cannot say that. It is proportional to the intensity of a vibrational transition, and is always non-zero when the two states have quantum number that differ by 1. So this option may be confusing for you, some of you, that whatever I have said here, that the from this specific selection rule is have obtained, that is delta n is equals to plus minus 1 or delta v is equals to plus minus 1. So this is the selection rule for vibrational transition. So this vibrational transition selection, from this selection rule, you can say that if there is a two states which differ by 1, then these two non-zero, this is always non-zero if this is satisfied. Okay. So from where this selection rule comes? Selection rule comes that under which condition this will be non-zero. This transition over integral is non-zero, and it was found that for delta n equals to plus minus 1, that is this n of f minus n of I is equals to plus minus 1. Under this condition, this is non-zero. Okay. So what is written, that it is always non-zero when these two states are differed by quantum number 1. Yes, that is correct. But it's always non-zero. This word is a problem because it is depends upon these two factors. If this is 0, if this is equals to 0, then 0 into something will be whatever. If it is 0, then whether it is 0 or non-zero, it doesn't matter. If it is 0, then your transition dipole moment, transition moment integral will be 0. So you cannot say that this fourth option is correct. So your correct option is, it can be either 0 or it can be non-zero, depending upon what is the value of d mu dx, what is the value of psi f star x psi I d tau. Okay. So for a diatomic molecule, this what we say that for a diatomic molecule, this transition dipole moment integral involving two states will always be can be non-zero, it can be zero. Okay. Okay. So I'm moving to the next question. Which one of the following statement is true about a system of two masses connected with a harmonic spring and having no external force acting on it? Okay. So the kinetic energy is proportional to the total mass of the system. The potential energy is proportional to the reduced mass of the system. The center of mass undergo harmonic motion. The kinetic energy can be written as a sum of kinetic energy of the center of mass and the relative motion of the atom. So I will going to find that. First of all, you can find this answer in this lecture number 31, where it was also discussed in the very first page that the kinetic of the energy of the system can be expressed as the center of mass and the relative motion coordinate. So I'll just explain it briefly. There was a detailed description that was given here there also. So what is started with, that there is a spring connecting these two bodies which have mass m1 and m2. Now what is the relative distance x? If it is at x2, m2 is at x2 and m1 is at x1, so we know this relative distance or relative coordinate is at x equals to x2 minus x1. Same thing for center of mass. What will be the center of mass? If we know the center of mass coordinates x, I can explain it as m1 x1 plus m2 x2 divided by m1 plus m2. Okay, so yeah, so I'm taking a new slide where I'm going to discuss this. Yes. So now I'm going to discuss this. So what is mentioned here, that I have mentioned that this is suppose of okay. If there is two bodies which have mass is m1 and m2, and you can see that if it is vibrating and if position is x1, its position is x2, so relative coordinate x can be defined as x2 minus x1. I'm just going quickly. And what about the center of mass? Center of mass motion will give m1 x1 plus m2 x2 divided by 1 plus m2. Okay. So you have to just you know to find what you need to find. You need to find this x1 in terms of x or m2. So from this you can go x2 is nothing but x plus x1. Just you put this here. And cross multiplication you do plus cross multiplication m1x plus m2 capital X is equals to m1 x1 plus m2. This x2 will be replaced by x plus x1. So I can write it as m1 x1 plus m2 x1, just taking this same thing here into x. Now you need to find what is x1. Okay. So for finding this, just a minute. Okay, so you can do that, or else you can do. So what will be your x1? You're taking m1 plus m2 into x, considering here, plus sorry. It will be minus m2 into x, and what will be in the denominator? There will be m1 plus m2. So how this is coming? You can clearly see if we take common from m1 x1, that will give, I will be left with m1 and plus m2, and m2x will be in that side. It will be in the opposite side of this equal sign. So what will be my x1? My x1 will be m1 plus m2 by m1 plus m2 into x minus m2 by m1 plus m2 into x. Okay, sorry, this x will be the small x. Okay, yeah. So this will cut out x minus m2 by m1 plus m2x. This will be your x1. Similarly, if you just put this value of this x1 in this here, and if you add this with x, you will find what will be the value of x2. I'm just not calculating that. I'm just writing this one as x2 is equals to x plus m1 by m1 plus m2 x. Right? So these two x are looking just equal. No, to use another symbol. Yeah. So these two are x will be there. So I have got this expression for x1 and x2. Right. Now what will I do? Now I am going to the expression of kinetic energy. Now I am going with kinetic energy. Kinetic energy is defined as half mv square, just m1 v. So okay, we just write it as x1 dot. You understand this? This is dx dt square plus half m2 x2, which is dot also squared. Okay. Now you have to put these values half m1. What will be the x dot x1 dot? You next to this, this will be suppose. So you can find this. So from x1 and x2 you can find this x1 dot, that is dx of dt will be equals to x dot, that is d capital X by dt minus m2 by m1 plus m2 small x dot. Similarly, what will be the x2 dot? X2 dot, that is dx2 dt, it will be the same x dot minus m2, sorry, so this will be m1 by m1 plus m2 to x. This will be dot again. Okay. So how is it is happening? If you take ddt of on the both side, your dx dt will be there, and if m1 m2 will be constant, so you will get dx dt, and this there will be, I am writing this as dot. Suppose so, dot signifies a dot is a dA dt. Okay. So it is beneficial if someone is confused with that. So if there is something like a dot which signifies that dA by dt. Okay. So x dot means dx by dt. Dx1 dot means dx1 by dt. So now I am just squaring it up. So x dot minus m2 by m1 plus m2, here this is another x dot which is squared up, plus half m2, there will be x dot plus m2 divided by m1 plus m2 into small x dot squared up also. Okay. So if you simplify this, I am not doing all the steps. You have to square it up. Then you will see that some terms will cancel out because m1, m2 is there. M1, m2 is also there. So I think it is m1. Not to be confused with m2. This is okay. I am writing it again. Don't be confused with m1, m2. This is m1. Okay. Again it is like same. So this is m1. Okay. So you have got this, and if you do this, you will see what will be your final expression. Your final expression will be left with half. What will be your final expression? Final expression will be half m1 plus m2 x dot square plus half m1 m2 by m1 plus m2 this x dot square. Okay. So you can see here there is only two variables. Okay. So m, if you just rearrange this m, so you will get everything in terms of x dot and x dot, small x dot and capital X dot. So if I express total mass of the system as m, so if I express total mass of the system as capital M, so I can write it as capital M x dot square, and the second term I would like to write as, it is called mu. You have seen it, mu is equals to m1 m2 by m1 plus m2, which is called reduced mass. So this is called center of mass, and this is called reduced mass. Okay. So what is the final expression? The total T is the summation of kinetic energy corresponds to this coordinate, this center of mass coordinate, and kinetic energy corresponds to, this is the kinetic energy corresponds to center of mass coordinate, and this is the kinetic energy which corresponds to relative reduced mass coordinate. So now I'm going to the question. that the kinetic energy can be written as a sum of kinetic energy of the center mass and the relative mass of the system or relative mass of the atom. So this is the correct answer. I have proved it. Okay. Okay. So next, I am moving to the next question. So you have to find the energy gap between two successive P lines in the spectrum. What will be the energy gap? So I'm just writing this rotational vibrational. I'm not writing everything which was also discussed. Just quickly, I am just expressing it. So you can find it in lecture number 28. It was discussed about the P branch and R branch transition. So a line in P branch has an energy associated with the energy is given by is nu bar E minus 2 nu bar E chi E minus 2B into G plus 1. Okay. So the next transition will be suppose from a P branch line corresponds to suppose in one P branch line there is a transition from V equals to 0 to V equals to 1 state. Okay. So as I have stated earlier that every vibrational state is associated with some rotational states. Okay. So if there is a transition from V equals to 0 to V equals to 1, then there will be a transition of J equals to 0, 1, 2, 2, J equals to J prime is equals to 0, 1, 2 or etc. Okay. And under this condition, your P branch transition will happen, and P branch condition is your delta J should be for P branch transition delta J is equals to plus minus. I'm sorry, this will be no minus here. There will be only plus sign. Delta J will be equals to minus 1. Okay. Yeah. So P branch transition is happening with energy difference delta J is equals to minus 1. Now, what about the next transition? If you see, this is the transition in nu bar. If it is the fundamental transition, this P branch transition will coming here, and under this approximation, this is the R branch transition. You can see this P branch transition, the lines in the P branch, they are equally spaced. And how is the spacing? Since your vibrational level, just understand the concept, since your vibrational levels are not changing for P branch transition, that is the transition from V equal to 0 to V equal to 1, so the change in the spectral lines will be only associated with rotational transition, right? Since your vibrational energy levels are fixed, you can see here your vibrational energy levels are fixed. Okay, you have taken two vibrational levels and you have just measuring the transitions. It need not to be V equals to 0, V equals to 1, it could be anything. But your two vibrational level will be constant, and then you are seeing what will be the change due to this rotational energy levels. Okay. So when you are seeing this change, you can see there is only one term will change, that is the rotational contribution. And you know for the transitions, the rotational energy gap is nothing but, it was discussed earlier, that is nothing but 2B. Okay. So 2B, 6B, 8B, like that. So it will go on. So if you put J equals to 0, you will find it is B 2B. This next one will be J equals to 1, it will be 4B. If it is J equal to 2, it will be 6B. So gap will be 2B, 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 2B kind of thing. So, and this is called P branch transition. This is called R branch transition. Okay. So your answer will be 2B. It is a very straightforward question. Okay, so I am moving to the last two questions. That is, which of the following is the correct relationship between the frequency of an harmonic oscillator omega and its mass, and you have to compare it with this K. So it is also a straightforward question. You know this answer, that yeah. So in reference 29 you can find that the relation between the frequency of harmonic oscillator and the spring constant is always given by omega equals to root over k by m. You can clearly see. So whenever you are writing your potential energy, suppose you are writing in terms of half a x square. Okay, this k, spring constant, is nothing but your m into omega. Hmm. Just a minute. K square equals to m into omega. Okay, so you can also verify that. And if you take this k, it will be root over of. Oh, sorry, what I am writing is completely wrong. Sorry for this. So you will get to some expression like half m omega square x square. Okay, so whenever you are using this convention, half m omega square x square, you can find that this omega square is equivalent to this k. This is the force constant. So from there you know that this comparison was made, that this force constant k is related to m omega square. Now you can rearrange it, that is omega square, I can write it as nothing but k by m. So your omega will be root over k by m. You have seen earlier that in one problem I have used this relation whenever I was utilizing to use this kinetic energy. Okay, so your omega will be nothing but is equals to root over of k by m. So this is the correct answer. Okay, so I am going to the last question, that for a transition metal complex COH stage appears at 1840 centimeter inverse. So you have to find isotope level COD stage will appear at where. Okay, so it is not a question from this week. It is a question with reference to level lecture number 22, that I have also discussed some question regarding that. But here only one information is missing, that you need to know the atomic mass of cobalt. So atomic mass of cobalt I have written here as 59 atomic mass unit. So you should try this to do with your own, and then you can see the solution. So I am doing the solution. You know that this is the relation 1 by 2 pi c root over of E by m. Just a second. So 1 by 2 pi c root over k by mu. This is the relation, or relation between vibrational frequency, vibrational wave number, and uh, this k and mu. Okay. So why am I using this relation? Because you can see all this stretching appears at using centimeter inverse, that is the wave number unit. So that's why I am using this nu bar. Okay. Now I am writing just nu bar of COD by nu bar of COH. Will find that you will be 2 1 by 2 pi c root over k by mu. Suppose, and what, why I am writing k, because these oh, no, I'm just want to ask that I can write it KCO or KCOH or KCOD, but I'm not writing KCO or KCOD. This is a mistake. I have written this should be K by mu COD. Sorry, this will be D. To find D, this would be H. Okay. So you can see this 1 by 2 pi c, 1 by 2 pi c we cancel out. So why I am not changing? What was the I asking that why k is not changed? Because it was already mentioned that when you are using any isotope, the bond length will not change. Since bond length will not change, so there will be no change in the force constant. Okay, because force constant depends upon the bond length and bond strength also. So since this is not changing when we are experiencing this isotope, so only mu will change. This k will unchanged, and then so we can cancel this k from this top and bottom. This top and this bottom, I can cancel this k. So I will left with mu of COH by mu of COD whole raised to the power half. Right? So this will be the expression. So first of all, I need to find mu COH by mu COD. So for this, I've had to find it separately mu COH. So I need mu MCO into MH by MCO plus MH. Just I need to put these masses. I've written the mass of atomic mass of cobalt is 59. So this is, don't confuse it with carbon monoxide. This is cobalt. This is cobalt. Okay. So 59 into 1 mass of hydrogen, you know, and this will be 59 plus 1. So this will give us 59 out by 60. Now I am going to do the same thing for COD. This will be m of CO into m of D divided by m of CO plus m of D. So what should be the change? The change there is that mass of deuterium will be 2, and this will be 59 plus 2. Okay. So this will be 59 into 2. I know its value is 118. This will be by 61. Okay. Now I have got these two values, my mu CO and mu COD, mu COH and mu COD. You just need to put this here. What will you do? You just put of mu of COH. So I need to put this mu of COH 59 by 60. And this is in denominator, so I am just writing it in the reverse format. This will be 118 by 61. So this is going to be 2. Okay. So 61 by 60. Okay. So approximately you can say that you can say this will become an all scale. So this will become half. So it will be almost 1 by root 2 times almost. So you can calculate it because 60 and 61 not that much different. If they are cancelling, then we are left with 1 by 2 over half. Okay. Now I am getting to this main equation. What my main equation says? Main equation says that you're just changing the color because this is the math. So final equation is nu bar COD by nu bar COH will be is equals to 1 by root 2. Okay, so if you do this for nu bar COD, you will get nu bar COH by root 2. Now it is mentioned as 1840 nu bar of COH. Just you need to divide it by root 2. It will give you nu bar of COD. So I have calculated that, so it will come nearly 1311. Nearly, or this will be some fluctuations for different persons. So your answer will be here, close value is 1300. So your answer will be nothing but 1300. Okay. So by that way, if you know what is the stretching frequency of a single particular stretching mode or COA here, what is meant under COH mode, you can easily calculate the stretching frequency of this isotope labeled compound. suppose cobalt is replaced by its isotope, cobalt's isotope, hydrogen is there. Now you can see that how this frequency will change. You can easily calculate what I have shown you. In this way, you have to find then CO mu of COH and you have to find then mu of COD. Just like there, you have to find some of COH and CO of other isotope of the CO and that of H. So from that you can easily calculate that and you will get to know what should be the frequency of this isotope level compound. Okay. So this is the end of today's lecture, so today's live session, where I have solved some problems regarding this rotational vibrational spectroscopy and the spectroscopic origins, which is coming from this quantum mechanics, how they are going to affect, how we're going to affect the spectroscopy, and how the spectroscopic terms, spectroscopic transitions, spectroscopic selection rules, all of these are derived from this uh, quantum mechanics. So from quantum mechanics, how they are related, we have discussed that, and we have solved a few questions where I have shown you that what is the, I have used so much the concept of ladder operators there, how ladder operators is related to the Hamiltonian of the system, and how Hamiltonian can be written in terms of this ladder operator. Okay. So in the next class, I will again solve some problems. Okay. So I'm making this session to an end. Since no one is joining, so I am stopping the recording.